Chapter 10, Complex Experimental Designs. Up until this point, we have discussed simple experimental designs, where just one variable is being added or subtracted, but experiments tend to be more complicated than that. One way we make an experiment more complex is by adding more than two levels of the independent variable. This allows researchers to learn more about the form of the relationship, not just whether a relationship exists or not, but how the amount of something creates changes. One example of this is a positive monotonic relationship, which is a positive nonlinear relationship between variables. The graph here is looking at the relationship between dart throwing and mental practice, essentially visualizing where the dart is going to land. The solid line examined this relation twice, once at 0 mental practices and again at 100 mental practices. Having these 2 points makes it look like a linear relationship. However, when you add in more levels, 25, 50, and 75 mental practices, you can see that this relationship isn't linear. And you can see that 50 mental practices creates the same outcome as 100. Again, you are gaining more information by having more levels. When you have more than one level, you can also see curvilinear relationships, where the relation among variables is essentially curved. This is a hypothetical graph showing low or high scores on a dependent variable as a function of 3 levels of an independent variable. If you only measured level 1 and level 2, it would look like a positive relationship. And if you only measured levels 2 and 3, it would look like a negative relationship. But having all 3 levels gives a full understanding of the relation. We can also increase the number of independent variables. As you can imagine, this would be more similar to real-life situations because there are many variables affecting how we behave. Say someone doesn't perform well on a test. Is it because they didn't study? Or is it because they experienced a high level of anxiety? When we increase the number of independent variables, we use a factorial design, in which all levels of all independent variables are combined. Maybe you would measure high and low amounts of studying with high and low self-reported anxiety. From this, you can get a main effect, the direct effect of an independent variable on a dependent variable, therefore answering the question of whether 1, studying affects test results, and 2, whether anxiety affects test results. But you can also get what's called an interaction, where the effect of the dependent variable changes depending on the levels of an independent variable. Maybe there is an interaction between studying and anxiety, such that if someone didn't study for a test and they have high levels of anxiety, they perform worse than someone who does have the same amount of anxiety but studied a lot. In factorial designs, variables might be manipulated or non-manipulated. For instance, you could choose whether you want to try to increase anxiety in a lab or just get a self-report measure. And the simplest version is a 2x2 design, which I will explain more in a moment. This is another example of a factorial design in a study examining how much someone eats when they're with another person eating. In this case, it was a person who worked in the lab called a confederate eating with a participant, though the participant was unaware of this. In this example, you have 2 levels of 2 independent variables. 1, how sociable the confederate was, and 2, how much food the confederate ate, making this a 2x2 design. From here, you can measure the main effects, see if high sociability versus low sociability influences how much a participant eats, and whether the confederate's food intake, again low or high, influences the amount of food the participant consumes. And you can then look at the interactions. Does having both high sociability and high food intake lead to different outcomes than being high or low on the other variables. This is a slide from before with an additional point at the ends. We describe a factorial design by the number of levels of the first independent variable by the x symbol, the number of levels of the second independent variable, third, and so on. So this can become more complicated with the number of groups you have. This is another example of a 2x2 design and how it can become more complex. At the top, this is looking at uniform color and temperature on athlete aggressiveness. At the top of that first table, you have two factors, dark versus light, and two factors of temperature, hot versus cold. But like we talked about at the start of the lecture, levels matter, and having something beyond a simple yes-no is helpful for better understanding the relationship. Therefore, we can make this a 2x3 design, where we keep the two levels of dark versus light, but add in a third level of temperature, making this now hot versus moderate versus cold. The more factors added, the more participants you need, because you need people for each of the groups you create. But the benefit is that you get a lot of information that will help you to see the relation among variables. As stated, there are different ways to examine the data you obtain. You have the main effects, where you look at just one of the independent variables alone on the dependent variable at a time. So just uniform color on athlete behavior, and just temperature on athlete behavior. And you do this by seeing if the levels of an independent variable differ from each other. Is there a difference between light versus dark uniform color on average athlete behavior? If so, there is a main effect of uniform color. The interaction is the combination among independent variables. Does an independent variable influence the other independent variable's effect on the dependent variable? This is where you get the "it depends" answer that is so common in human research. If you ask the question, does uniform color affect athlete behavior? And someone says, it depends. How hot is it outside? That is an indication that there's an interaction here. And being able to say it depends and get the context of the situation is really the main benefit of a factorial design. The data obtained from factorial analyses are analyzed using a factorial ANOVA. This works much the same as the ANOVAs you are familiar with. It's measuring mean differences among groups. The difference is that this is measuring mean differences among each and every group, including each subgroup. So you get an F ratio and a p-value for each main effect and each interaction. Factorial designs can be between or within subjects, which again works just like before, but with more groups. If you have an independent or between subjects design, you have different subjects in each group. You have athletes in light colors and athletes in dark colors. You have athletes in cold temperatures and athletes in hot temperatures. But you could make this a repeated measures or within subject design, where the athletes participate in each condition. They first wear light colors and then change into dark colors, or they first play in cold and then play in the heat, or vice versa. So each person experiences each category. You would need fewer participants for a repeated measures design, but you can imagine that it becomes complicated for the researcher to implement. And lastly, you can have a mixed factorial design, which includes aspects of both categories. Maybe you're interested in gender, which you cannot assign as a researcher, so that is an independent factor. But participants all go through the same conditions like a within subjects design. For this week's activity, come up with an example of a 2x3 factorial design using the hypothetical experiment that you submitted last week. You can make it more complicated than a 2x3 if you want, but only if you want to. And be sure to list 1, each main effect, 2, each of the possible interactions, and 3, how participants will take part in the study. Will this be independent between subjects, repeated measures within subjects, or a mixed factorial design? And be sure to explain this. And just as a side note, you do not have to add this to your experimental presentation. This is just to provide you with some structure and guidance so you're not stuck trying to think of an example. And then also to help you think more deeply about the experiment that you submitted last week. And if you have any questions, as always, feel free to reach out.